Today's lesson will be one of our longer lessons we've had for a while, so I'll just ask you to get fired up and stay with me as we go through this. We'll be looking at functions. We have several objectives to cover today. We want to observe the relationship between functions and relations. We'll introduce domain and range. We'll define a function formally. We'll represent a function 5 different ways. We'll learn about the vertical line test. We'll talk about function notation. And we'll graph a function by plotting points. So let's start by observing the relationship between functions and relations. Let me preface this by saying before we jump into functions and relations, I want to talk to you about a topic that I think most of you will be familiar with. Do you remember the other day I showed you a picture of my grand dog Remington? She's a black lab, and I'm going to use her today to help us try to understand a little bit better the relationship between functions and relations. Let's begin by looking at a pyramid here, in which the bottom layer is dogs, the next layer up is labs, and the next layer up is black labs. Now, I think most of you, if I said to you, can you understand the relationship of this pyramid, you would probably say yes. If I said to you, is a lab still a dog, you would say, sure it is. If I said to you, is a black lab still a lab, you would say, absolutely. If I said to you, can something be a black lab and not be a dog? You probably would say, no, that's not possible. For it to be a black lab, it must be a lab and it must be a dog. If I said to you, are there some characteristics that you could use to identify dogs that should be labs? You might talk to me about the length of their hair, how big they are, the size of their feet, the shape of their heads, the way their ears do. There are all sorts of things you could describe that would help me understand the difference, say for instance, between a lab and a chihuahua. So, today what we're going to be looking at are what are those characteristics that can move you up this pyramid. Well, we're going to look at it though in terms of mathematics. The pyramid looks like this: relations, functions, and one-to-one functions. The same characteristics hold true for the pyramid on the right as it does for the dog pyramid. Some relations are functions, some functions are one-to-one functions. And what we'll be looking at today are what are the characteristics of relations that make them functions. We won't be talking about one-to-one functions, that'll come later on this semester, but I wanted you to see the full pyramid here to kind of get this concept in your mind. Let's now talk about functions and relations. Every function and relation has a domain and a range, and they're connected by some sort of correspondence. Those terms are terms you need to get used to: domain, range, and a correspondence, which pairs the items in the domain with the items in the range. Let's talk about the definitions now of a relation and a function. The definition of a relation is: a relation is a correspondence between the domain and range such that each member of the domain corresponds to at least one member of the range. Before we discuss that any further, let me go on and give you the definition of a function, and then we'll compare the two. A function is a correspondence between the domain and range such that each member of the domain corresponds to exactly one member of the range. Let's look at the differences between these two definitions. There are some key words that are in boldface type. Notice relation has the words at least one, and function has the words exactly one. And those are the differences, but sometimes it's kind of hard for students to get their minds around. In order to help you understand the differences between these two definitions, I've come up with a game. Now, I use the name game loosely because truly I do understand that this is not incredibly entertaining to play this, but it will, however, help you understand the concept of a function and a relation. What I'd like to do is give you a domain. It's a set of names: Maria, David, Megan, and Jasmine, and a range made up of colors: blue, green, and red. The correspondence we'll be dealing with is car color. And so let me put in some arrows here now so that you can see how the domain connects to the range. You see Maria, David, Megan, and Jasmine. Now that we have the correspondences in, here's where the game begins. Trust me, this is a little bit more entertaining when you're a classroom full of students, but since you're at home by yourselves, we're going to have to pretend that you're playing along. What I'm going to do is I'm going to call out a domain element. That means I'll be calling out a name. You'll need to follow the arrow and respond with the appropriate color. So let's play. By the way, I'll be skipping around, so stay on your toes. Ready for the excitement? Here it comes. Jasmine. Red. David. Red. Maria. Blue. Megan. Blue, green, turquoise, teal. And if you hear the confusion there, it's because you're not exactly sure what to respond with. Megan, the domain element, is paired with two different range elements. In other words, you're not sure where to go when I call out Megan. That means that this is not a function. It is just a relation. Let's play the game again, and I'll make a change. Same domain, same range, correspondence is still car color, and here come the arrows. Our question now is this a function? So let's play the game again. David, red. Megan, green. Jasmine, red. Maria, blue. And what you should have noticed is that every time I call out a color, you knew exactly what to respond. And by the way, thanks for responding. I could hear that. So what we have this time is every name I called out, you knew exactly where to go. And so what you find is this is a function. Let me remind you, it's still a relation, remember, because that's in the bottom of the pyramid. But it is a function. Now, that little game, silly though it may seem, will truly help you as you make your way through the rest of these functions that we have to look at today. Our next thing is we're going to look at 5 ways to represent a function. They are verbally, we'll look at a table of values, we'll look at a diagram, we'll look at graphs, and we'll look at functions that are defined symbolically. So let's begin with a verbal representation. If I ask you to add 2 to x to obtain y, here's how the game would work. I'm going to give you a number, you're going to add 2 to that number, and you're going to respond with that answer. So here we go. If I say 2, you would respond with 4. If I say 6, you would respond with 8. And if I say 8, you should respond with 10. And that's exactly what you've done. What we have now is a function. Let me ask you, how do you know it's a function? Because every time I gave you a number, you knew exactly what to respond with. If I gave you 8, you didn't have a choice of whether or not you were going to respond with 10 or 12 or 14. You had to add 2 to that 8, and every time you did that, you got a 10. So therefore, there was only one choice. Every time I gave you a number from the domain, you had one choice to respond with from the range. Therefore, that is a function. Let's now look at a table of values. I've got a table here, and I've got x's on the top and y's on the bottom. Let me remind you that the domain will always correspond to your x values, while the range will correspond with your y values. So we're going to play the game again, and place down your toes because I will not be calling these out in order. So let's ask the question, is this a function? So here we go. If I call out 6, you respond with 4. If I say 9, you would respond with 13. If I say 5, you say 7. If I say 1, you say 2. If I say 3, you say 2. Now I want you to notice, every time I called out a domain element, you knew exactly what to respond. The fact that you answered 2 twice is not an issue. It's only if you know where to go every time I call out a domain element. Since you did, on this one, know where to go every time, the answer is this is a function. Let's play the game again. The question is still, is it a function? We have domain elements and we have range elements again. So here we go. Let's play the game. 9, 3, 10, 7, 6, and you're not sure which 6 I'm looking at because I'm skipping around. You don't know whether to say 9 or to say 4, and that's sufficient right there for you to be able to tell me that that is not a function. The next thing we want to look at are diagrams. This will remind you of the one we've already done. We start with the 2 circles here, and let's put in our arrows, our correspondences. The question is that a function? Let's play the game. 1, 2, 3, 4, 5. Hopefully every time I called out a domain element, you responded with a range element. Did you have to make any choices? If the answer to that is no, you had no choices to make, then this is indeed a function. I want to talk to you now about a vertical line test, because a vertical line test is what we use to determine if a graph is that of a function. So let's look first of all at the vertical line test, and then we'll look at some graphs to apply it. A graph is a function if it is not possible to draw a vertical line that intersects it more than once. By the way, vertical is up and down or across? Vertical is up and down. So here we go. Let's take some graphs and let's look at these. The question is, are these graphs functions? For the first one, let me remind you what the vertical line test said. It said a graph is a function if it's not possible to draw a vertical line that intersects it more than once. So let's draw a vertical line. Let me ask you, how many places does it intersect the graph, or in this case the blue line? Only once. So that doesn't rule it out as a function. Let's take that vertical line away and let's draw another vertical line over here. This time, how many places does the red line intersect the graph or the blue line? Still only one. So, is it possible anywhere up and down that line to draw a vertical, a straight up and down line that would touch the blue line more than once? The answer to that is no. Then what you would say to me is that it is a function, and let me give you the reason for that. It passes the vertical line test. Let me say that one more time. This graph is a function because it passes the vertical line test. Let's move to our next graph now, and let's draw a vertical line over there. Here I have a vertical line that touches that graph in how many places? Well, I strategically placed that one so that it touched the graph only in one place. But the question is, can I draw a vertical line anywhere that would touch that graph more than once? Well, let's move the line over here. Now let me ask you, in how many places does the red line intersect the blue graph? Twice. I see two different places. By the way, let's just make sure we're all looking at the same thing here. I see an intersection here, and I see an intersection here. So those are the two places that the vertical line intersects the blue graph, and so this is not a function. Let's continue now to a symbolic representation. Y is equal to 2x plus 3. The question is this a function? Well, the easiest way to determine that would be to graph it and apply the vertical line test. You should know how to draw that graph. If not, you can always do it on your calculator, but you should be able to do it by plotting points as well. But if you'll enter it on your calculator quickly and graph that, you should see this graph. The question then is it a function? Can you draw a vertical line anywhere on that graph that touches the blue line in more than one place? The answer is you cannot, so yes, it is a function. Now, I want to clarify something for you here. Once you know this is a function, you need to name it in such a way that whoever comes behind you will also know that it's a function. Let me give you an example. 20-something years ago, we didn't do ultrasounds the way that a lot of people have them today. So when I was pregnant, we said, hey, we're going to have a baby. When the baby was born, not knowing what it was, we had a boy's name picked out and a girl's name picked out. We waited. When the child was born, we looked at it and we said, well, golly gee, it's a boy. We better name him Michael instead of Jamie. And that's exactly what we did. So let me make sure you understand. Once we know that this relation is a function, we need to give it a name so that somebody who follows along behind us will know that it is a function. We can name it f of x is equal to 2x plus 3. Notice that the right-hand side of this stays exactly like it was. So this part over here doesn't change at all. What changes is instead of writing a y, we write f of x. Please make sure that you understand that is not f times x or anything like that. That is actually the name of a function. Whatever letter is used right here is the letter that should go here. And this is whatever you would like to call it. For instance, I could have called my child Michael, I could call him Mark, I could call him John, I could call him Paul. Here we can call this f of x, we can call it g of x. This part right here is just a name. This letter corresponds to whatever letter is used as your variable. Now, how does that function notation work? Let me remind you of something you already know. If I gave you this relation, y is equal to 2x plus 3, and I ask you to evaluate it when x is equal to 4, what you would tell me to do would be plug that 4 in, then you would multiply there and you would get y is equal to 8 plus 3, or y is equal to 11. Well, let me show you the beauty of function notation. If I know this is a function and I want to ask you to evaluate it, I simply tell you to plug a 4 in for the x. When I say find f of 4, I'm asking you to evaluate the function when x is equal to 4. From there on, your steps are identical to what you did on the left-hand side. So once again, what you would tell me is f of 4 is equal to 11. Now, we want to be able to graph a function by plotting points, and you should say, well gosh, isn't this what we did before? Because graphing a function by plotting points is no different than graphing a linear equation by plotting points. Let's just review quickly how that works. If I give you this function, f of x is equal to 3x minus 5, and by the way, I know it's a function because its name says it is a function. To graph this function, we want to start by building our t-chart, and because there are no fractions in this, I will choose 0, 1, and 2 as my pick numbers. Remember how we did this with linear equations. I would say let x equal 0. Well, this time I don't need to say that. I need to say find f of 0. That means do exactly what you did before, plug in a 0, and we would get negative 5. That would go in our table. I would do the same thing for f of 1, and I would get a negative 2, which goes in the table, and I would do f of 2, which would give me 1, and that goes in the table. You'll notice I'm moving through this much more quickly this time because hopefully by now you understand how this works. Our graph would look like this when we plot our points and connect the dots. I know that for some of you the material we covered today may be new and it may be a little bit more confusing, so I want to leave you with this quote by Johann von Neumann. He said, "In mathematics you don't understand things, you just get used to them." I hope at this point you're at least getting used to them. I'll see you soon. Bye-bye.